Hello everyone, this is Arun Mahendrakar. I'll be in this lecture. We'll learn some tools from real analysis. Right? So basically, these are the mathematical preliminaries required to understand this course on nonlinear analysis. So we'll touch upon just the bare essential mathematical tools that are required to understand this course, right. So we'll start with real number, right, set of real numbers. We will denote it by the script R, right. Now let n be any integer, right, greater than 0, and now what you do is you form a set of, you take a set of real numbers x1, x2, so on up to xn, where each xi is a real number, right, and then you arrange them in an order, right, x1, x2, so on up to xn. So what essentially we have done is we have started with a real line, right. We picked a real number, we picked n real numbers x1 to xn and then arranged them in a orderly fashion, right. And when you arrange this in this order, right, we call it as a vector or a point, right, in n dimensional Euclidean space, right. So we have constructed a vector using real numbers, right, and in fact the definition of Euclidean space follows by collecting all such points, right. The collection of all such points or vectors is called the Euclidean space, right. So either we call x as a vector, we will denote it like a column vector, right, or we can say this is a point in Rn space, the n dimensional Euclidean space. So what is this Rn space? It is the Cartesian product of n real spaces. We will denote it by n dimensional Euclidean space, right. So we have a vector now, right, in an n dimensional space. This was the idea given by Riemann, who until Riemann Euclid, we had Euclid's postulates, right, we had the work of Descartes. So all their work was confined to the plane geometry. Riemann was the first to think of imagining numbers beyond the 2-dimensional plane. So this is how you generalize a notion of a point or a vector in an n-dimensional space. So this is a real vector, right. So we will use the notation x belongs to Rn to say that x is a vector in an n-dimensional space. Okay. Now once we have this vector, we can do some operations on this vector. So if x and y are vectors in Rn, right, then we can add these vectors, we can add vectors. And how do you do that? So this is what we want on the left hand side, and the way you get is you write down the components, right, correspondingly for the y's, and then you add them component wise. So this xi's are called the components are components of the vector x. Components, or sometimes we also call them as coordinates, right, or coordinate. Xi is a coordinate of the vector x. So, you do a component wise addition, right, that is how this left hand side is defined. One can also do scaling, right. So, alpha is a scalar belong to real number and x is a vector. You can do a scaling of the vector by scaling each of the components. This is how you do the scaling is defined, right. So, note that the Rn space is a vector space, right. You add vectors, right, it is closed under the operation of addition. When you add vectors, the resulting vector is also a vector in the n dimensional Euclidean space. What other operations we can do? Well, we also need the notion of the origin of the Rn space, or the what is the zero vector, the trivial vector, or the trivial vector. Right. So, the trivial vector 0 is nothing but the vectors, the vector whose all components are all 0. Now, as I said, we can do some more operations using this vector, and we can think of what we are already familiar with, and that is the notion of the dot product. So, one can extend the notion of dot product on a n dimensional Euclidean space. So, we use a special name for that, we call it as inner product of two vectors . So, the notation is angular brackets. So, this should be read as inner product of x and y is nothing but x transpose y, or in terms of components it is the summation I equal to 1 to n xi yi. So, for n equal to 2 you have this is the usual dot product, or for n equal to 3 you have the usual dot product that we are already familiar with, right. But this is it captures the notion of inner of dot product in an n dimensional space. Now, once you have the notion of inner product, right, and also you have we have defined the notion of the 0 vector, we can talk about length of the vector. We want to talk length of a vector x in Rn, or we want to capture the notion of distance between two vectors. Right. So, both these notions, either the notion of length of a vector or the distance between two vectors or distance between 2 points, right, is captured by the mathematical term called norm of a vector. Right. What is this? The norm of a vector is denoted by the vector with two parallel lines, right. What does it do? So, it is a mapping, right. So, we denote the norm of vector by norm of x, and what does this norm do to the vector? It takes a vector in Rn and gives you a real number. In fact, it gives you a non-negative real number. Because it does not make any sense to talk about distance being negative, right. So, we will denote it by the symbol R plus for the collection, the set of all non-negative real numbers, right. So, we are familiar with some properties of distance, right. So, let us see whether they hold for this object that we have defined called the norm of a vector, right. So, before I list out the properties of the norm of vector, let me give an example of what is known as an Euclidean norm. So, this is one way of defining a norm, Euclidean norm, right. So, x is a vector in Rn. So, the symbol used is you put a subscript 2 to say that you are using an Euclidean norm. The 2 comes because of this square terms. So, you take the components, each of the components, you square them and add them up and then take the square root sign, right. So, this 2 comes from the taking the square of the components, right. So, this is one way of defining a norm. So, this is called the Euclidean norm. So, I use this symbol to define an object, right. So, one can define a norm, right, which may not necessarily look like this, right. However, whatever norm we come up with, it should satisfy certain properties, which should be consistent with the idea that the norm captures the notion of distance between 2 points or the length of a vector, right. So, let us see the properties of the norm. So, this properties of the norm, it applies to any norm, right. So far we have just defined the Euclidean norm, but shortly I will define some other types of norm. So, as we have seen, the norm is a mapping from Rn to R plus. So, the first property is, right, the positivity property, that means the norm of x, right, is equal to 0 if and only if the vector is the trivial vector, right. So, that means if you show norm of some vector is 0, that means the vector has to be identically equal to 0, and conversely if you take a 0 vector, its norm is 0, right. And norm of x is positive whenever x is not equal to 0, right. So, this is what we understand, the length of a vector is always a positive non-negative quantity, right. It is 0 only when the vector is a 0 vector. So, this is known as positivity property. The second property is about scaling. Norm of alpha times x, right, where alpha is a scalar, is nothing but the absolute value of the scalar times the norm of x. Right. So, this is the scaling property, and the third property, which is the most important property, is the triangle inequality. What does it says? For every x and y in Rn, norm of x plus y is less than norm of x plus norm of y. right. So, these are the three properties for this function to qualify as a norm. So, as I said, one can come up with your own definition of norm, right, as long as it satisfies these three properties, right. So, as an exercise you can check that the Euclidean norm which we defined earlier satisfies all these properties. So, as I said, I will give you more examples of norm, right. So, there is something known as the P norm which sort of generalizes the class of norms that one can talk, and as a special case when p equal to 2 you have the Euclidean norm, right. So, for p greater than or equal 1 but less than infinity you have the P norm. So, x is again a vector in Rn is defined as, so you take the components, raise it, take the absolute value, raise it to the power p, right, so on for all the components, and then take the pth root of the resulting expression, right. So, this is known as the P norm. So, one can talk about one norm. So, one norm becomes just the sum of the absolute values, right. So, two norm we have already seen, we get what is known as the Euclidean norm. So, for p equal to infinity we defined this is known as the infinity norm. So, it is defined as the max over I of the absolute value of xi, okay, where I varies from 1 to n. So, we have seen the notion of a norm of a vector, right. We have seen the properties of the norm. So, when does a norm, when does this function, right, that we have defined qualifies to be a norm, and as I said one can come up with your own set of norms as long as it satisfies properties 1, 2, 3. Right. Now, we earlier defined the notion of inner product, right. So, let us see what is the relation between the inner product and the norm of a vector, right, norm of two vectors. So, we have so let x y belong to Rn, right. So, we have the inner product between x and y, right. Now, this is a scalar. So, we can take the absolute value. When you take the absolute value, it is related to the norm of x and y through the following inequality. That is, the absolute value of the norm of the inner product of two vectors x and y is less than the norm of x times the norm of y, right. So, this is known as the Cauchy-Squarce inequality, very useful equality which we will use when we do the stability analysis. So, in this inequality becomes an equality if x and y are linearly dependent, right. So, if x is some beta times y, then you have the, then we have the equality. So, we dealt with the notion of a vector in an Euclidean space, an n dimensional Euclidean space, right. We talked about adding a vector, scaling up the vector, the notion of zero vector. Then we also introduced the notion of inner product which captures the familiar notion of a dot product between two vectors. We also saw the how to capture the length of a vector by the notion of norm or distance between two vectors, right. So, we also saw the relation between the inner product and the norm through the Cauchy-Squarce inequality, right. So, with this we are now in a position to define topological concepts that we will require during this course. So, the notions that we need to understand are as follows, right. So, these are topological concepts drawn from point set topology. So, to begin with, we need the notion of open ball, which leads us to the definition of open set. So, once we have the notion of open set, we can talk about closed set, and then bounded set. When is a set said to be bounded? This also leads us to the notion of compact set, very important notion in our analysis, right, very powerful property it has, compact set. Then we also need the notion of dense set, and we will also need the notion of connected set. Okay. So, these are building blocks in when you study topology, point set topology, right. And with whatever notions that we have already studied, the norm of a vector and the inner product, right, we should be able to define all these sets, right. So, the objective is that we should know the definitions of this set, how the definitions are built. We should also be able to identify when is a set open set, when is it closed, right, when is it compact, right, and so on. This is the objective of understanding the math preliminaries behind this course. Right. So, we will begin with the notion of open set. So, to do that, we will require the notion of open ball, right. So, an open ball in Rn, right, is again a set. It consists of it is a ball of radius r, strictly positive. So, and centered around a point x, right, and we will denote it by b x comma r. So, x is the center of the ball and r is the radius of the ball, right. So, it consists of all points in the Rn space such that the distance between x and y is strictly less than r, right. So, you see that the points to be noted is, so we talk about a ball of radius r centered at x, right, x is some point given to us, and we collect all points such that the distance between x and y is strictly less than r, right. So, we call such a set the open ball with center x and radius r. So, to picturize, to visualize this in n equal to 1 dimensional, right, that is in the real line. So, you have a point x, you have a radius r. So, it consists of all points which are distance less than or equal to r. So, all these points on this line constitute the elements of the open ball, right. So, here the open ball is denoted by this limiters, right, the round brackets, right. So, it so the interpretation is that it consists of all points except the point, the end points, right. So, these points are excluded from this open set. You can visualize this same open ball in R2, right, in 2 dimensional, where x is now the center and r is the radius, right. So, this picture when we talk about ball is very clear to us, right, but we should be able to extend this, the idea of open ball in an n dimensional space. For example, in n equal to R3 you have the 3D ball, right. So, here I talked about these round brackets. So, here instead of the brackets I have a dotted line. So, it consists of the n ball, the ball with center x and radius r, right. It consists of all points, right, except the points which are marked dotted here, right. So, all these points belong to the ball of center x and radius r. Sometimes I use the notation in this, or this is the same as this notation, right. So, once we know the notion of an open ball in an n dimensional space, right, we can define the notion of a open set, right. So, a subset A, so somebody gives you a candidate set, a set A, right. So, a set A is said to be an open if for all x in A, right, for every point in A there exists a radius which could depend on that point x, right, such that the ball with center x and radius r, right, is contained in the strictly contained in the set A, right. So, let us understand this. For example, this is the by set A, right, and where if you see this dotted line, it means the set does not include those points, right. So, is this set open? Well, let us take a candidate point. We took a point x, right, and then we are able to come up with some radius, right, centered around this point, such that all of these points is contained in the set A, right. Now, you go very close to the dotted points, you can always find a small ball of arbitrarily small radius such that all its points, right, are contained in the set A. So, this set A is an open set. Now, come to the picture on the right, the set B, where the set also includes points, this unlike the set A, all the boundary points are also included. Note that there is a mathematical definition of boundary, we have not still introduced that, but we understand what is meant by the boundary from the picture, right. So, we will later on give a precise definition of what is meant by a boundary of a set, right. So, for the time being we will take that these are the boundary points, right, and if you pick a point x on the boundary point, no matter how small the radius is, right, if you draw a ball around that, right, I can take even a smaller ball, right, not all points in that ball, right, are elements of the set B. So, the set B is not an open set, right. So, to understand this notion of taking a point, right, and coming up with a ball, all of whose points should belong to the set, right, is better captured through the notion of the interior point. So, let us define what is meant by an interior point. So, we have a set, let A be a subset of Rn, okay. For simplicity, when I am drawing pictures, either n is 1 or 2, right, but the definitions holds for any dimensional space, right. Now, I want to define the notion of interior point of A. Let x belong to A, okay. Then x qualifies to be an interior point of A if there exists a ball with center x and some radius, right. That means, if there exists a radius r positive, right. So, with that you build up this ball Bxr. So, there exists a ball Bxr such that all points in Bxr belong to the set A. So, I have a set A, okay. Suppose I take a point x, right, and I can always find a ball of some radius, all of whose points belong to the set A, right. So, the challenge really lies in taking a point very close to the boundary, right, and then can you find a radius r such that all of these points in this ball belong to the set A, and the answer is no, right. So, this word interior sort of captures that things will go bad, right, when you are on the boundary of the set. However, things are nice inside the set, nice in the sense that you will be able to come up with a ball such that all points in this ball belong to A, right. So, the set of all such points, right, constitutes the interior of a set, right. So, the set of all interior points of A is called interior of A, denoted by I and int A. Okay. So, here in this definition we took a point x, we saw that we could come up with a ball, right, all of whose points belong to the set A. You take another point y, right, you will be able to come up with a ball, all of whose points belong to the A, right. So, collect all those points which satisfy that condition, and that collection of all that points is called the interior of A. Right. Now, how is this related to the open set, the definition of open set, right. So, a word of caution. So, if you look at this definition, the key phrase is if there exists a, right, that means you have to come up with just one ball, right, such that all points in that ball belong to set A, then that point x qualifies to be an interior point, right. It is not required that for every ball around that point this property holds, right. So, we will see how one has to be careful with these phrases, right, in interpreting the definitions. So, now we are in a position to define the notion of a open set. We earlier gave a definition of open set as if you can find an open ball which is contained in the set A, right. So, a set A is said to be open if all its points are interior points. That is, A is nothing but the interior of A is nothing but the set A. So, examples in real line in R, open sets are open intervals. We saw that earlier. For example, take this open interval 0 1, right. So, this is called the open interval because it excludes points 0 and 1, right. So, in R this is an example of an open set. In R2 you can take any center, right, with a ball and some finite radius, right. So, all the points in this except the boundary points, right. So, it is an open disk. So, in R2 the open set is nothing but the open disk. Open sets are open disks, right. So, it consists of all points except the boundary points, right. So, you saw that to define the notion of open set I require the notion of interior points. So, once you identify the interior, once you understand the notion of interior points, right, you collect all the interior points and that gives you the open set, right. And if you can show that the interior of the set A is nothing but the set A itself, then A is open. Now, we want to define the notion of closed sets, for which we require the notion of complement of a set. Complement of a set, right. So, A is a subset of Rn, right. So, A complement, right, is all those points in Rn except the points in set A, right. So, one can also define this using the notion of set minus. So, what is this? This is the symbol for set minus. So, if I have two sets A and B and if I have a non-empty intersection, then A minus B, or also denoted by A minus B, is nothing but all points of A, right, without the common points. So, in this example, this is the A minus B, right. So, the complement of the set A is Rn minus A, right. So, if I have a disk here, right. So, the complement is of this set A is all the points other than the set A, right. So, in the real line the complement is, so the real line is minus infinity to infinity, right. So, from the real line you take out, say if I have 0 1 as the open interval, right, as a set 0 1, then this is nothing but minus infinity, right, to 0. So, this square bracket implies that it is it includes the point 0 union 1 infinity, right. So, this is the, if I call this as A, this is the complement of A, right. So, once you understand the notion of complement of a set, it is easy to define the notion of closed set. The closed set is nothing but a complement of an open set, right. So, closed set is nothing but complement of open set. So, one may ask, can I define the notion of closed set just like the way we define the notion of open set using the notion of interior points. So, can I define some other concept, right, give it a property and then say that collection of all those points is a closed point, right. So, one can do that and we will see that in the next lecture. Thank you.